recording? All right. So, I boxed them out here, and let's just kind of work our way down the list. So here you have your kinematics. We're not really working with those. It's not that you're not going to use them. It's just that it's not the focus of this unit, right? The focus of this unit is going to be on these boxed ones. So yeah, you may still need to use Newton's second law. You may still have to use constant acceleration kinematics, but for the most part, we're looking at force and its relationship to momentum, right? Which is includes describing the impulse. Okay, so J is your impulse. Just making sure you understand, at least at the cursory level, what each of these letters represent can help. I tell you guys, you don't have to memorize the equations, but especially with how the algebra works out, it really helps to memorize the equations. If you know them, then as you're trying to do your systems of equations, it's like trying to put a puzzle together without having all the pieces. If you don't have it memorized and you get to a spot where you need that equation and you don't remember it, you're not going to know that that's a puzzle piece you have available to get on to the next step. So it can really help to memorize these and understand how they fit together. One thing to know about momentum is that whenever you deal with momentum, you have to deal with net force. Okay, your net force is the one that causes any sort of momentum change. So for example, if you have simply just a box resting on a table, you can have multiple forces involved, normal force up and gravity down, but none of these are actually changing the momentum of the box. It's not quite the same as energy, where you can say one is adding momentum and one is taking away momentum. It doesn't make sense that way. It doesn't really work like that. So you really put all your forces together first, then you can figure out what the momentum change is going to be. Yeah.
So if it were moving, how would you say? Would you say this force is causing it to move in this direction by this much, or would you just say all of the system and momentum changes this much?
All of the forces put together result in a net force that will then cause it to move in a certain direction, and if it's pushing on it over a certain amount of time, that will result in a certain amount of momentum change.
Okay.
Yeah. That's you have to look at it as the whole system. The whole system. And this kind of goes two ways. Either you have a force, a net force, and then therefore the momentum will change. Remember, don't forget that this is all vector stuff, right? So you can have wherever direction the net force is pointing, that is the direction the net momentum will change. If your force doesn't change, or if you don't have a force, that means that you can't have a momentum change. And that is also a very useful scenario where you have something like a collision. We talked about collisions and explosions, where there's nothing else really pushing or pulling on it, just these two things interacting together. And if you treat them together as one system, then you can talk about how its initial momentum will equal its final momentum, right? And that is also a very useful application of conservation of momentum. Don't forget, conservation of momentum is a consequence of Newton's third law, right? So in other words, if something gives 5 Newton seconds of momentum to an object, it must lose 5 Newton seconds of momentum in that direction. That's the conservation part. Yeah. Okay. Any questions about momentum, what it is, how to calculate it? All right. Yeah, Newton seconds. Newton seconds. Or if you want to do kilogram meters per second, that can work too.
Does that make sense?
Okay. Now, the next unit was on work, right? So if Chapter 9 was momentum, Chapter 10 and 11 is about work and energy. And we talk about how there's a conceptual side of energy and then the calculation side of energy. You should always take a step back from what you're doing and make sure that the conceptual, qualitative side of the energy makes sense with the math that you're doing. So is it really demonstrating conservation of energy, whatever. So the work done, right, that is, you take your force, and then you do it over a certain displacement, and then you put them together, you get work, right? So This is maybe not the easiest way of using work because you got this force and this integral thing, and it's not written here, but most of the time, if your force is constant, if the angle's not changing, and you're displacing in the same direction, you're just pushing a box or you're just sliding along, this essentially just becomes force times displacement. Usually, as long as it's in the same direction, the angle's not changing, your forces, everything stays constant except for the change in position, then you can do that. The other thing that's different about work and from momentum is you can talk about work of a particular force while having multiple forces acting on something. You can talk about the positive contribution of work from one force and the negative contribution of work from another force. So it's like adding and removing energy. It makes sense to talk about adding and removing energy. It doesn't really make sense to talk about adding and removing momentum like in the same way. That doesn't really work. Yeah.
So for the work, if we're going in the negative direction, would you say that forces are contributing in
It's not the direction that an object is moving to have negative work. It is the relation between the direction of the force and the direction of the movement. If the force is in the opposite direction of the displacement, it is doing negative work. So if I push forward, I am doing positive work. I'm pushing it in the direction it's moving. If friction is trying to slow it down towards me and it's still moving forward, I have friction towards me, but its displacement is away from me, then friction is doing negative work. Right? It's all about which direction force is with respect to the displacement. That's how you determine if it's positive or negative work. Okay, this is just kinetic energy. You don't have to memorize how to derive it, but it's good to know that this is derived from just Newton's second law, using the chain rule trick. Right? That's where it really comes from. Power is just the rate of change of work, or the rate at which you're doing work. So you can talk about the power of friction acting on something and the power of whatever gravity we're acting on something, all the same thing. This one is a specific form of power, the same way this is a specific form of work. You can use this only if your force isn't changing, your velocity is not changing, your angle is not changing, and this essentially just becomes this. So sometimes you'll come across these simplified scenarios and you can use that. But this is the more general form of it. This is gravitational potential energy. You can only use this if your mass is not changing and gravity is not changing. So you can use this close to the surface of the Earth, or if you talk about a different planet near the surface of whatever that planet is, you just can't be changing positions very much. Any height change of more than like 100 kilometers, and you can't really use the same one, right? So we're talking about orbit, of low Earth orbit, or the upper ends of low Earth orbit. You can't really do that. That's where this one comes in. But for this one. But for this unit, we're not using this one. This is for when we get to universal gravitation. We start talking about escape velocity. We start talking about, planets orbiting stuff. We're not there yet. That's different. That's a special topic. So on this equation sheet, there's the UG here and a UG here. Don't use this one. I'm not saying don't use this one ever. I just mean for this test, it's not relevant for this test. Don't use this one for this test. Same thing with kinetic energy. Don't use this K for this test either. This is rotational kinetic energy. We haven't dealt with any of that yet. This I omega squared, don't try and force you.
Like the same thing, but
Oh yeah. Yes, it's a rotational analog. It really is, right? 1/2 mv squared, 1/2 I omega squared. So this is like a rotational velocity. So this is like a rotational mass. And we'll see how that works out. But
There's not going to be anything rotational.
not on this test. There's nothing rotational on this test for once. Next unit is 12, which is all rotation, like all of
Shoot me now, please.
this. Actually, literally all of this is rotation. From here down is rotation.
That's a lot of equations.
Yeah. You should recognize some of these. Torque,
Yeah,
you should know that one. Centripetal stuff, you should know that one. This one. This is rotational kinematics, so it's really like 4 equations here you don't know.
That's a little better than what I was like looking at earlier. I was like,
Yeah.
we're
Just
done
wait
for-
till we get to E and M. We still have all of this. for E and M.
Also, we got all of that other one.
See all this calculus going on here?
I love calculus.
We'll get to that
Calculus is fun. Come on, guys.
later on.
You know it's life.
Yeah. Mechanics has minimal calculus. There's like 2, maybe 3 integral derivatives here. Okay. Lastly, this is all spring stuff. Okay, if you're wondering what the S is, that's for springs. This is Hooke's law. Hopefully you remember what K stands for. K is the spring constant. It's a measure of the stiffness of the spring. And then this gives you the potential energy of that spring. You should know these two.
How many watts are in a megawatt?
1 million. Jinx. Alright. Any questions about these equations, how to use them? Will?
For these spring equations, just to verify, is x the distance from the equilibrium point?
Yes. X is from the equilibrium point. So, not the length of the spring. Be careful about that. I think I was extra careful. I was extra careful. I used S for the distance of, which includes the length of the spring, but this X is just a displacement. Good. Any other questions? All right. Let's do a couple example questions. We'll start from easiest, and then we'll work our way up. No, I'm making up some.
Thank you.
Would you prefer to use the homework?
I've already done it.
Um,
No, I wasn't complaining. I was just wondering.
Yes, you are.
all right.
You were about to complain. I was just-
Never mind. Senor is
Because I'm lazy, I don't want to write this all again. I'm going to use some covering cards here. Okay. So, consider, for example, what does this look like to you?
a beaker? Is that a beaker?
It looks like a chicken.
I thought it was a beaker.
That's the second person who said it looks like a chicken.
I thought it was a beaker.
Huh?
Oh, I see. It's a cannon.
It's a cannon.
Haven't you watched enough cartoons, Matt?
That's what cannons look like.
No.
You have to have the defined wheel, and then you have to have the cannon after.
No, not all cannons have wheels. They have. See, okay, what does that one look like?
We can't say.
That one.
That's a cannon.
That's a cannon.
See?
No,
It's literally the same thing. That one's inked up.
the top one is curved differently. No. See, the bottom one is symmetrical, but the top one isn't symmetrical.
It has a big behind, all right?
Yeah.
It's well endowed.
Look like a cannon.
I see the chicken now.
You see the chicken with the hair?
It looks like a vase. That's honestly what it is.
Alright.
I saw a picture and I was like, the beaker exploded.
Anyway, so
Man, our deductive skills.
this cannon,
Good team.
firing a cannonball straight up. I'm gonna say that here, use that as 0 potential energy at the top of the cannon. Okay, so you have to always set a reference level, right, when you talk about potential energy. And what I want to do is, how do we figure out how high it can go without using kinematics, but using energy? It ends up being the same thing, which it should. It'd be weird if it wasn't. But I just want to go through the steps that I'm taking in my calculations. Frankly, in the last 2-3 units that I've gone through, each unit has had kind of like a particular process, right? When we did kinematics, it was always set up your kinematic equations, right? Is it change in x equals to the 1/2 at squared and all that stuff. You start with the general equation, and then you start substituting in information that is relevant. Same thing with Newton's second law. Still has some of you guys, even on your corrections, are not starting with Newton's second law. You guys are jumping right into setting forces equal to each other without starting with F equals ma. And it's very dangerous. It's dangerous. Not dangerous like life-threatening. I just mean
It is.
It is.
Or it is life-threatening.
it is very prone to mistakes. If you just try and make things equal to each other without setting up the equation in the general form first, because a lot of times what happens is when you set things equal to each other, you make assumptions to get to that step. And a lot of times I see students make assumptions for one problem and then make the same assumption on a second problem where that assumption can no longer apply. And that's where the mistakes come. So it's the same thing here. Start with the general statement, which is a statement of conservation of energy, which is hidden, that your initial kinetic and potential energies should equal to your final kinetic and potential energies. Now, the only way you can say this is you have to assume, you do still have to assume a couple things. You're assuming that there are no external forces. Oh, that's right. Actually, I am skipping ahead a little bit. I'm going to pause and go back for a second. There were a couple equations that weren't on the equation sheet that we did talk about in class. Let me revisit those super quick before we move on. It was about this, the different kinds of work. They didn't really mention this in the equation sheets. And so that I don't overwhelm you, let me cover some of this up. So, focusing on that first. All I have for So, right, the work kinetic energy theorem says that if you take this equation and you add up all the work done, that will result in a net amount of work done, and that is directly related to how much your kinetic energy will change. What we said is that we don't have to take all the different kinds of forces and find some sort of net force every single time. Sometimes it's convenient to keep them separate but categorize them. The same way we categorize normal force, friction force, gravity, tension, so on, normal force. Maybe I'm saying that twice. So in the same way we kind of can break up work can be done by these different kinds of forces and different kinds of work. You have like a conservative work. Okay, conservative work done by conservative forces. The easiest main conservative forces to know about right now is gravity and the spring force. Those are conservative forces because it's the way they behave. Usually, they're only a function of position. Okay, so if you imagine connected between you and the Earth was a rubber band, right? And that was essentially gravity. And that as you went further away from the Earth, you are stretching this rubber band, right? So it's like storing energy in this gravitational rubber band, and then when you come back down, you're releasing that energy. That is kind of the nature of conservative forces, is that they work against you when you move in one direction, but they work with you when you go back. They give it back. They give back that force. They give back that energy. The only thing that's different about gravity for this model, the MGH model, is that it's like a rubber band that pushes on you with the same force all the time, no matter how high up you are. Turns out that's not accurate. The further away you get, you do actually get a weaker force, but we'll get to that later. Anyways, but that's kind of the hallmark of conservative forces. They push in such a way where you kind of have this storing effect in one direction and a releasing effect in the other direction. You don't really get that from like dissipative forces, like friction. You can't ever get the energy back from friction. It's always dissipative. It's always working against you no matter which direction you move. And then same thing with kind of external forces. External forces is kind of a grab bag of every other kind of force: normal force, tension force, compressive forces, whatever it is. It's just an applied force, essentially. If you push on something, that's like an external force, or normal force, something like that. So conservative forces are like special forces. They're special because of the way they behave. You can always write some sort of potential energy function for them. And potential energy works in this negative delta U way, where when that force, like gravity, is doing positive work, you are expending that potential energy. And when it's doing negative work, it is storing that potential energy. So it's like this storing, releasing aspect.
So there's a whole other category of you saying conservative force ability over water.
Yeah, we're categorizing. We're saying, okay, you're special. We're going to count you separate from all the other forces. And then we have dissipative forces, and we also say they're special. They're special because they're the kind of forces like friction and drag that always push in the opposite direction of which you're displacing. You will never have friction or drag push in the direction that you are displacing. Yeah, not the direction you're accelerating, but the direction you're displacing. If you're actually changing position from here to here, drag will always be pushing this way, and friction will always push against you. It will never be the other direction.
Like a car, you said the car uses friction to go forward. So
But that's a little different because that's not the displacement of the thing that is experiencing the friction, so to speak. So like that's also really hard to say because it is not usually for propulsion like that. That's like at the moment, at the point of contact, it's stationary, so you don't actually have any displacement. Like static friction never does work because it's static, no displacement. So static friction never does any work. Rolling friction is also kind of tricky too. But anyway, I'll qualify it with saying generally speaking, most of the time, friction and drag will work against your displacement. So we'll just say it's like a negative work. And then you have everything else. And so when you put it together, we can kind of put it all on one side and say that if there's any sort of external work done, so if you push on something, or there's normal force, or there's tension, pulling or pushing on something, that energy, or not just pulling and pushing on something, but pulling and pushing on something to cause it to move. It needs to actually move, right? Work requires an actual displacement. There's no actual energy transfer unless it actually changes place. That energy can either go into speeding it up or slowing it down, go into storing it, or it can be dissipated and turn into thermal energy. And any combination of these changes will change the total energy of your system. Okay? So, yeah, this can be positive or negative work. Positive work can go into speeding you up or being stored or making it hotter, or if work is done against the system, it can slow it down, it can remove potential energy, or it can cool it down. I know that seems kind of weird.
we can make it less hot.
Yeah. A piston is kind of a good way of thinking about doing this. Yeah, actually, it's like you forcefully expand the gas.
Yeah.
Yeah, and it can cool it down. Okay, so what does this tell us? When you talk about conservation of energy, this is kind of like the skate park problem or simulation in the homework, the FET skate park. Basically, you have a skateboarder that's in a half pipe, and it's just like going back and forth with no friction. Actually, let me just bring it up, because my drawings are clearly insufficient. So it looks something like this, right? So you got a skateboarder, and if we have no friction whatsoever, and we just let her go back and forth, right? So the idea here is the total energy is not changing if we count. See how gravitational potential energy is not considered an external force. Gravity is not considered an external force.
Because it's part of the
It's we count conservative forces as kind of part of the system. Yeah. I mean, you can create a model where it is not part of the system, but then you're going to have energy going in and out of the system in a very regular way. And it's kind of weird to do it that way. So it's much easier to count it as part of the system so that in this case, there is no other forces acting on on the person that is doing work. There's gravity and there's a normal force, but the normal force is always perpendicular to the surface, which means it's always perpendicular to the motion, which means that the normal force in this case does not do any work. Okay? And so the only thing that's doing work is gravity. And we transform that gravitational work into this potential energy function so that we can see how it's increasing, decreasing, increasing, decreasing. So its total energy stays the same. Now, I can manually do work on the person, right? And then I can increase the potential energy